Chinese language. Okay, so this class is mainly going to concentrate on, there's going to be 6 main ML methods we're going to be working on, but it's the one that's the big revolution in the last 15 years is CNN. It's kind of the Swiss Army knife that can solve many different problems, and that's what we use. We often have to use another ML method with our CNN, as I'm going to show you later, to get things to work just right. What's the difference between neural networks and convolutional neural networks? Say, let me say right here. This guy typically involves 2 operations. What 2 operations does a neural network or convolutional neural network require? Marco. 2 simple mathematical operations.
The matrix vector multiplication.
Matrix vector multiplication.
And a nonlinear function.
Then some nonlinear function, which you call a threshold function. And the threshold function, someone asked me, they didn't quite understand that. You can think of it as kind of like an all or nothing function. Unless the output of this matrix vector multiplication, let's say the output was 1, 2, and then we have this threshold function, and the threshold function is one that is a point-by-point threshold function. When you apply it to a vector or a matrix, it applies that all or nothing operation to each individual element and returns the same size vector as before. So if we had an all or nothing, like this is my z, this is my sigma z, and I had an all or nothing like function like that, what number should be here? Marco. Marco or Marcos?
Co.
Is there an S or just no?
No, just the O. 0 and 0.
0 and 0. Why? Because this has an input of 1. This is the Z. Has an input of 1. 1's working over here in the nothing regime, so the output is going to be nothing. And same thing for 2. Now, why are we doing that? Well, they're trying to emulate the brain because the example of the child learning to not touch the stove, you don't want that the neuron that says touch the stove, if you have an electrochemical potential with a value of, say, greater than 0, say 1, it's going to touch that stove. So you want something when you have all these inputs, there's a 1 brightness, prettiness, warmness, 10, all these inputs come in here. You want to make sure that this guy is really overweighted, and when you do a sigma, the weight will be a -1. You don't do it explicitly, you learn this. W, the weight, times -10 is going to put that into a -10 category. And if you add everything else up together, the total summation is going to be probably something less than 0, -5 maybe. Well, -5 is not going to survive that all or nothing function if the all or nothing function only admits things greater than 0. Now, typically we don't use something so sharp. Why, Marcos?
Because it's really
if you're a mathematician, you would say
it's discontinuous.
Yeah, because the derivative of this doesn't exist at this point. It's discontinuous. You want something smoother than that. And in fact, the brain might work this way as well, although I read something recently, a new model of the brain is using these all or nothing type functions. Okay, so
What about for the backpropagation issue?
Pardon me?
For the backpropagation, it's difficult to take derivative of functions that are not continuous.
Well, there's ways to handle that, I think. Okay, well, see, Marcos knows more than your average somebody who doesn't know anything about this area. He uses a magic word called backpropagation. That's a special way of saying taking the inverse, right, Marcos? Okay, so, then the last problem. All of you have heard this last 10 years, the great revolution of machine learning. Andrew King, one of the wonderful teachers, as well as he's been the president or CEO of Baidu, B-A-I-D-U, Chinese something or other company. He was a research manager at Google, and he quit all the jobs, and now he's doing something else back in California, I think. He has a phrase, ML is the next electricity. Back in the 1800s, the late 1800s, the world changed when all of a sudden you started wiring up the continents with electrical cables and started using electricity to do a lot of jobs that normally took a lot of labor. So he thinks that machine learning is going to be in a very similar way. It's going to spread throughout society quickly, and in some areas it's definitely quickly spreading. So, but why is it doing it? Because we went from neural networks to convolutional neural networks, and why is that a magic? Why is that so special?
Complexity is reduced.
By computational complexity reduced from every time you do an iteration, you got to at least do one giant matrix vector multiply. Not only in the forward iteration, but the backward one that he called back propagation. And to do a matrix vector multiply, and this guy is on the order of millions by millions in size. So what's 10 to the 8th squared, Marcos?
10 to the 8th.
No, 10 to the 8th squared.
10 to 16.
N is 10 to the 8th. It's a 10 to the 8th by 10 to the 8th matrix. Doing a matrix vector multiply, it's roughly going to be 10 to the 16th algebraic operations.
Yes.
For one matrix vector multiply. There's no way you're going to be able to do that even on an exaflop computer. But you need thousands of these iterations. And thousands of these tens of thousands of these matrix multiplies to do a solution. So what's the big change? And a matrix vector multiplication costs you n squared operation, cap n squared operation. Cap n is the number of rows here, say a square matrix. What's the number of operations to do a matrix vector multiply? Marcos?
16, 32.
What?
32, 10 power.
N squared. N squared.
So 16 square should be like
yeah, okay.
a lot.
It's a lot. But if you only have to do convolution, that's roughly on the order of n, because the filter length for the convolution is very small, the order of 20 or 30 points. So you ignore that number. So convolution only costs you kappa n. I mean, on the order of n operations, yeah.
Does this ill conditioning of the coefficient matrix also play a role? Because if you have to have a full matrix, you have to invert all the n square elements, which needs much more data. It means that the inversion is more ill conditioned.
Yeah, often your problems are ill conditioned. That is, lots of models can satisfy almost the same data. So that's something we'll address in more detail, but that definitely you have to do that. That will even happen with convolutional methods.
Yeah, but conventional you reduce that for order of n squared to order of n, so you only care less coefficient to be inverted.
Yeah, that's one way of looking at it. If that will work, if the convolutional model works, that's related to the problem at hand. Turns out the convolutional model seems to be a pretty good model for how the brain works as well. We'll give you details of that later to convince you that might be true. Okay, so enough of the review. Okay, we have these funny, whenever you see something like this is one layer, and deep learning is how many extra layers do we need?
5 or more.
I've seen someone say greater than 5, but usually nowadays probably the bar has been raised to maybe greater than 10 or something. But we get by with about 5 to 10 layers. And we get by with maybe on the order of maybe about 100 or so neurons per layer. The rule of thumb is, and we'll get into this in more detail, is the deeper the network is, usually the faster your convergence. The deeper the network there is, the more robust your method is. The thicker your nodes are, each layer, thickness, height, thicker that if you just use one of these, you're going to increase the complexity of the model and a very complex relationship between input and output. You need that kind of thing, but just one layer alone with lots and lots of neurons is not going to be enough. There's a theorem that shows that. It says you're going to be spending a lot of time waiting for convergence. So to reduce that problem, you bring down the number of nodes in one layer and increase the depth of your network. And that'll increase not only your robustness, but your conversion speed. We'll get into that. Okay, enough of that. So if you see something like this, it just means that there's a complex engine here, a complex brain that they've devised. You're going to see more representations of that. That connects the input to the output. And this happens to be just a time series as your input. Each node here is the amplitude of this time series. This is time increase in this direction. This is the amplitude that you're throwing in at each node. It's like an image, a 1D image. And you're trying to decide something about what this is. Does this indicate an exoplanet, or does it indicate something else? And I'll show you an example of that. Okay, and the something else is a yes or no. Exoplanet, yes. You have one here. So it's a classification problem. A no is a not exoplanet. Okay, so let's look at some examples. Sure enough, we're going to look at the examples of hunting for exoplanets by the Kepler telescope. The Kepler telescope was launched in 2009, and what it does is stare at a patch of stars, typically within 100,000 light years of our own planet. It's to look for dimming of the stars that are periodic. Because when a planet, when you're looking at a star, this is your star, and it's very bright. But when you have a small planet circling it, the planet blocks some of the light, and the light you are looking at dims periodically. And that period is related to the period of your planet orbiting the sun. Now, of course, if your star's like this and your planet's looking like this, you don't get any dimming if you're looking this way, right? So you got to have special planets where the planetary rotation is in a plane that is parallel to your line of sight. Okay, so that's how they look for planets with this Kepler. And they'll look at patches of the sky for years at a time. And the reason they look at for years at a time, because the periods of these planets range anywhere from, say, a week, couple of weeks, to maybe a couple of months. And you got to get enough of these rotations that appear through the noise to be able to convince yourself you do have a periodic dimming of these, the light that you're looking at. So you look at this piece and this piece and it keeps going. And there's a picture of your Kepler telescope, launched by NASA. And there's a zoom view of what they're looking at. And one of these is this star system, this galaxy, it's a solar system. They call it TRES-2. And it stares at it. And of course, it stares at all the other stars simultaneously. It has all these little pixels in their imaging device that stare at different parts of the sky simultaneously. So here's the sun, and just showing you what it looks like. Look, there it is. There's our planet. And look below here. I wonder is a PowerPoint. And there's what this axis says is the brightness dimmed over time and then came back. And then they look for this over and over again. They stack this series. You get terabytes of data every week. And a normal human or a group of humans just going to go nuts trying to petabytes of data, try to examine what's going on here. So you'd like the computer to be able to look at this. It goes round and round, as the clocks indicate. And what they've done since 2009 with the Kepler, they've discovered planets by normal means. You have Earth-based telescopes that stare at things for a long time. In fact, we were going to be part of that program last year. I tried to get the dean to approve some money to be part of put a exoplanet. I don't know if anybody saw that talk about 2 years ago, 1.5 years ago, by the guy from Hawaii, the astronomer. Anyway, there's a program where I would buy a Earth-based telescope and stare in my backyard night after night after night, and then these amateurs or people like me would be able to find these planets. Anyway, so people like me would find planets like this, but when the Kepler finally analyzed a big chunk of its data, boom, it shot up the discovery rate tremendously. You know, from just a couple dozen to over 4,000 now. We have over 4,000 solar systems discovered that have exoplanets. And there is some actual data for one traverse. Okay, and so how do they analyze this? Now they're starting to analyze this by neural networks. And they have two neural networks. Well, there's two branches of the neural network. This branch analyzes the long scale time and your time signals, and this branch analyzes the short scale time. You want to make sure it's long scale time because if you have a long period in your planet rotating by that's their sun, then you don't want to miss that. But also, you want the short scale as well to fill in details in case as a confirmation that this is true. So they probably had other types of features as well. This happens to be 2 features in the paper I was reading. And it brings it in through this machine we call the convolutional neural network to make it fast. I think it's convolutional neural network. Although if they have these few nodes and these few layers, you can easily do this by a neural network as well. And then the answer is it an exoplanet or not? So tell me, what's your name? What? Shupeng? Okay, Shupeng. What do they do? What are the 3 steps for training the network? What's step 1?
Input, output, we should know.
Okay, so that is you look at the archives where you know you have input data and whether they're exoplanets or not.
Yeah.
And so you train your network to get what? The W's, the coefficients in that.
Get the coefficient W.
Okay, what's step 2?
Step 2, model evaluation. We should confirm like we get the success model that for the future general application.
Okay, what's that
give
called?
me a new input and you give me
Okay, so that's called testing.
Yeah.
He took this data that we have ground truth, broke it up into 90% for training,
Yeah.
and it could be changed at 70, 30. 90% for training to get the W's, and just to make sure you didn't overfit, we'll talk about that. You take that W you found and take that 10% you never trained on,
Never.
never trained on, but you know the ground truth to it, and he's going to apply it and see if it gave you the right answers. If you get something on there, I think they got about 95% or more accuracy rate. And once you do that, then you feel confident that, hey, data I've never seen before, hopefully it's not too different than what you've already done, will now be used to tell you whether it's an exoplanet. Now you can imagine all of you probably have massive amounts of data or problems that you're working with now that you can use a technique like this, or you can think of something in your area where you have vast amounts of data you think it's just hopeless to try to analyze it. But there is hope. This is petabytes of data, petawords. Okay. 10 minutes to 5 hours on one CPU, that's how much it takes to do training on the background data. Average results from 10, so you need 10 different copies. So you took 10 different copies of this apparently, and then stacked it together. So you get a lot of jitter, you get error bars. To make sure that this is you just don't give them one sighting, you give a stack. And 513 out of the 670 stars that were candidates. Looks like they had a probability of greater than 0.8. And what happens is, like I said, your desired is either 1 or 0. What usually happens is you get a number between 0 and 1. Anything above what you decide is the best, you can interpret that as a probability, and I'll show you that later on in the course. Anything above 20, that must be reliable. Anything below that. So they did catch things that were 1.5 apparently. They rejected everything but the 513. Anything less than 3 transits, forget it. Anything less than 29 minutes, forget it. And so your typical 1 star, you look something like this, you get the jitter, and then you get the error bars, and then you get a basket red line there that, and that happens to be something with a 14.5 day period. That this thing was really clear, there's 14.5. And the radius of the star was 1.3 times that of the radius of the Earth's revolution from the sun. So I think it's about 90-some million miles from the sun. So we're talking about 1.2 million miles from their sun. Okay, now here's the interesting things. A new one was found last year. No, not last year, last spring. By a student, an undergraduate student. And this is at University of Texas. And she found this one, 90i. And how did she find it? She took a class like this, and she got interested. And there's online codes in the paper. And she took the online data, online codes, adjusted it. And she went ahead and found the new planet by reanalyzing some of the data. And she looks like someone from grade school, but she's an undergraduate at the University of Texas at Austin. I guess it made a big splash. This is the Austin newspaper this last spring. So, one of the nice things about machine learning is the unwashed masses can do it. It doesn't take more than a class like this to get started in this. In fact, my daughter was a filmmaker, and she started taking computer science for the first time last fall to get a master's. She never had computer science before. This summer, she's had 3 machine learning projects, and she and I now talk the same language, as opposed before we didn't talk the same language. In fact, we're involved in I'll tell you about, we now have a joint project, my daughter and I. She's not here, she's in the States. Okay. Now, instead of looking for exoplanets and satellite images of exoplanets, let's now look for GPS markers of drone pictures. And this project came up last year when I taught this course, which is last fall. And there's a company on campus, and it got started at KAUST about maybe 8 years ago. And what they do is they get hired by various companies around around the country. And they take photos and they do all kinds of measurements with the photos. Like, for example, in Medina, they go ahead and Mecca, they take photos of the area, and then they map out the buildings and the roads and everything in high detail, and do other things for the municipalities that pay them. So they have all kinds of projects. They're a very successful company. But the big problem with their company is when they do a survey, they literally record hundreds and hundreds of photos, high resolution photos. This is on the order of 10,000 by 10,000 pixels, I believe. And they get hundreds of these things. And the problem is they have to calibrate these photos as to where their GPS marker is. And the GPS marker out of a 10,000 by 10,000 pixel is only on the order of 20 or 30 by 30 pixels. So it's a very small dot there. And they told me, and that they is my buddy Luca. You know Luca, Marcos?
Also, yes.
Okay. He told me it takes them weeks to be able to analyze these photos where that little marker is. And it drives them crazy. So I said, well, I think machine learning can do something about it, because they can find exoplanets, we can find little GPS markers. So I assigned it to one of my students, and I learned a lot from that. My student did just straightforward CNN on the photos that Luca gave us, and completely failed. They had tens of thousands of false positives. That's not good. So then I gave it to one of my advanced students, and he started adding in some new tricks to it. Now it's almost foolproof. He gets it every time. It takes just less than probably a couple minutes on a fast computer for one photo. So what you should take weeks now, in theory, could now take just minutes to find these GPS markers. Okay, so what's a GPS marker look like? It's about a half. I think it's about a half a meter, or maybe about a half a meter, about a 2 foot by 2 foot object, and it has some X with white in the middle and gray on the other part of the box. And they lay it on the ground, and they know the precise GPS coordinates to centimeters of where that is. They need that for calibration, registration of their photos. Where is it right there? Well, it's buried way deep. Do you see it there? Can you imagine having your job in this company trying to find that little dinky dot down there? You certainly would need glasses after a job like that. Well, Shihang is the guy who did this. So here's another picture. Anybody know where the GPS marker is? Shihang. Where is it? This just happened a small portion of a big photo. Who knows? Okay, so here it is, finding these, there it is right there. You zoom view into this, it comes out like that. Now do you see it? Yeah, if you look real closely, you can see that little baby. So this is not an easy job. And there it is. Can you imagine? for the rest of your life looking for photos.
So they have the picture with the GPS marker,
Right.
and the convolutional network help them to understand where it is in the picture.
Say again?
The convolutional neural network help them to detect where is the.
Where is it?
Hmm.
Find it without any false positives. 1 month for thousands of images is what he told me, as I recall. CNN plus, like, okay, CNN is what you already know, and this is the extra ingredient we use to make it really work. And that extra ingredient is basically a clustering method, which is one of the 6 ML methods we're going to talk about this semester. So often, to really do real world work, this alone often doesn't work. You got to add some more stuff to it. And this is an example of that. So I learned a lot last semester. So I figured, well, this should be simple to do. I found out, no, it's not. You got to use other tricks out there. Okay. By the way, one of the things we're going to talk about later is how you have to balance out the data for training. That is, you have 1,000 pictures, and you're training your network to recognize dogs and cats. But there's only a couple dogs in those set of training pictures, and the rest are cats. You're going to have what's called an unbalanced input data set. And it's going to lead to what Yu talked about. Many possible solutions to give about the same amount of air. Remember the air? Oh, I didn't draw that yet, did I? Okay. So you have this huge ensemble of pictures. There's 10,000 pictures. You send it through here, give you a yes or no. And there's only one dog picture, and the rest are cats. And you're looking to see what are the cat pictures. Okay. Well, if somehow, because there's only one dog and 90,999 cat pictures, it doesn't matter if your network makes an error and thinking a dog. That's a cat. It'll label that as cat. Why? Because it looks for the total amount of error of all these pictures. If you only make an error once out of 9,999 times, that's not much of an error at all. It's going to go ahead and find a W that will mislabel that as a cat. And the error, if it mislabeled this as a cat, but then I can find another set of W's that will label this as a dog, but maybe mislabel this as a cat. This is a cat. Oh, I'm sorry. It'll label this as a dog, but it'll label this as a dog as well, even though it's a cat. The same error. Why? Because in this case, the W's only made one mistake. In this case, it got the right dog, but it saw a cat as a dog, so it only made one mistake as well. You can imagine there's many different W's that will give you the same kind of rate of error. One mistake out of 10,000 tries. And that's because many models, many W's, many sets of W's, different W's, can give you about the same amount of error, right? But on the other hand, if you had a balanced data set and half your data were dogs and roughly half were cats, then you have a pretty robust system, even though it can make one mistake out of 10,000 tries. Big deal. Most of the time it's going to give you the right answer. And that will lead to a well-posed system of equations that has what they call a good condition number. And this is, you might not understand this in detail right now, but this is what Yu was talking about with a well-conditioned set of equations. You can fix that partly by balancing out your data set. And that's what I mean by that. 100 patches of, look at patches here, and you artificially put in pixels, and then you get the same number of patches without the pixels, and you use that as your training set to get the W's. And epic is simply the number of complete iterations of the whole data set. You have 14,000 patches as your input. And you go through that with one CPC set iteration entirely. That's called one epoch. Epoch. And they did 50 iterations of CPC set. And as what's your name? Shupong said, you divided the data set in the training set, and then you had a testing set. And 92% accuracy in the training set, and then had about the same accuracy with the testing set. In this case, it was an 80-20 mix. It took up 100% of labeled data. You have to label this data, right? It's easy to do because he artificially put in different views of these GPS. Sometimes you look at a GPS marker from this, and then sometimes you look at straight up. So you have to put in these different orientations of GPS markers. Yeah.
I have a question about the balanced and unbalanced data.
Yeah.
So we are sampling to make the training data set to make them balanced. But what if my validation, my prediction data set, for example, I just have one GPS in.
That's okay.
That's okay.
That's,
it will not.
That's exactly the real world situation.
So
but you want to make sure that these are the W's you've already trained on. Okay, it'll recognize that little GPS marker. You're not going to redo your W's. You're going to stay with those, and they should be able to work even if you have an unbalanced testing set over here. Because that's the real world. The real world's going to have unbalance. In this whole picture here, there's only one GPS marker.
So Professor, what happened, okay, if we have the training accuracy, 95, but for the validation accuracy, very low?
I'll talk about that.
Okay.
It means you overtrained, you overfitted your data. I'll give you an illustration.
So whether have you adjust the architecture or increase more data set?
Okay. We'll get into that in more detail. So you've overfitted, so you're definitely going to have to start reducing the complexity of your architecture. Fewer unknowns. And I'll give you an example of that to make it more clear. Okay, so here's his results, the typical picture. This is the first result I'm going to show you is what my student, and he's a first year student, so understandably, I thought this would be easy. I said, just do it, it's easy. Take one of the codes we have and do it. Oh. The yellow mean possible GPS markers. There are literally thousands of these GPS markers that we had to examine for the real one. Oh, wow, what's going on? I thought, well. And there's the real one. So there's literally thousands of false positives. But then he did some tricks. He used another ML technique, which I'll talk about later. It's called clustering. And he added that to the CNN algorithm and got it down even more. Then he added another trick I'll talk about later. And it's called SLIC, or simple iterative linear clustering. And broke everything up, not into big square pixels, but into cluster devised, what he called superpixels, and made sure that the boundaries of these superpixels never intersected the object of interest. And there's a trick to do that, to make that work. It's part of the SLIC package. And he's able to then isolate that. And he's able to go from tens of thousands of false positives to thousands of false positives to 0 false positives. I was able to get the actual one. Actually, had 5 false positives in the huge original picture, but once you saw what they were, you can easily build a little discriminator and tell you which ones, the GPS marker, which ones. Okay, so that was a success. Any questions on that? Yeah.
Can you give me a rough time that you can detect this?
What?
The time.
Minutes.
Only minutes.
Once you have the tough part is training for the W. That's going to cost you. That's hours on a multi-processor computer. But once you have this, if you have a GPU, one GPU in your laptop, bingo. This is probably less than minutes to go through this What problem are you interested in, Marcos?
What problem?
Yeah, what are you working on? What's your research problem?
I'm not working in machine
Okay,
learning.
you
I'm
don't
doing
work.
applied mathematics.
Are you she?
Yes.
Okay, she. What are you interested in? Oh, you're the machine learning expert, right?
Yes.
Oh, forget it.
So
He knows more than I do about this stuff.
have you some kind of like find the estimate the porosity of a reservoir through machine learning?
So what's your input data
Input data are like the data over on the wells,
on the well?
and I want to infer the porosity in the mid between two wells.
Well, I would say that, again, your input data should be not only the well data, but also seismic data to help you
Yes.
with interpolation.
Yes.
And so you need ground truth, and the ground truth is this is porosity here, porosity there, and then there's a certain kind of wiggliness that's special here. That's very different than the wiggliness of your other migration images here. And so you use this ensemble of data, and maybe not just the actual wiggles, but you use some characteristic signature, like the frequency band pass filter, the highest frequency within this zone here.
Yes.
So that's called a feature. Usually just the raw data itself is a poor man's way of doing things. You need features that you think are really important that distinguish porosity seismic sections from non-porosity. So I put in, I'll talk more about this in another example, but some features in here. And then you have a whole ensemble of data with no porosity, and those seismic signatures might be more something like that. I mean, you don't know, but you just have all this data. And your data, this is an image, right?
Yes.
You flatten the image. And in addition to the image, you have important well log information. You add that well log information to your big supervector. Okay? And then you train on that. And each pixel here is, supposedly you know the ground truth. So this is yes, 1, 1, 1, 1, 1, 1, 1. Okay, so that's your input, and the ones and zeros is your image for the output, your classification. Okay. Interpretation. 3D seismic image, those who are not familiar with this is a seismic cube. It's really like you're taking a big cube out of the earth and then kind of breaking it up into pieces, a vertical oriented pieces and a horizontal oriented piece. These dark colors correspond to where the boundaries of different geological layers are next to one another, and horizontal. Like when you go by a road cut, you're driving through a road cut through some mountain pass, you can look at the sides, see the faults, and see the layered boundaries. So that's the job of an interpreter in their own companies, or other people who are interested in subsurface structures. And you'd like to turn this guy into interpreted geology. Each color corresponds to a different type of geological piece of information. And that will typically take months to do, if not longer. And one interpreter will take months. But if you have a team of 30 or so, it might take just weeks to interpret that big 3D data set. So the companies are always trying to save money, especially after downturns. And usually a downturn, after they fire everybody, I've read that when the economy comes back, they'll replace the people they fired with technology. And this is one of the technologies. I'm sure the oil companies are doing like that. So it is a good thing that all of you are learning how to do machine learning, because when they do that, people are not going to be hired back or they're going to be fired. But if you have a pedigree with machine learning in the background, you can start becoming first on the list of being either hired back or maybe not being fired. And in theory, and it hasn't happened yet, as far as I know, you can have 3 hours let a machine do interpretation. Of course, you're always going to have an experienced person come by and look at his or the machine's answers to see how reasonable it looks. Okay, I was at a conference this spring, and the top person at Shell, who's in charge of I think he's in charge of it, in charge of the machine learning effort and interpretation at Shell Oil Company, one of the largest oil companies in the world. He's a very laid-back guy and doesn't like to say a lot. And he gave a talk on machine learning. I talked to him afterwards in private. I said, look, how far are you guys so far? Is it a real win yet at Shell? Machine learning for interpretation. He said, no, not yet. Is it going to be a win? He looked at me, he said, I've been doing this for 2 years in a big group. We have a group of about 20 or 30 people. He says, we have very interesting results so far. And I said, will you come to Cal and do this same lecture? Instead of mine, I was going to have him come. He said, so get back to me. So I got to his big boss, and the big boss said no. And you know what that means? It means it's probably it looks really good. Because if you hear an oil company person give a public talk, it usually means something that they've already done that if it works, everyone else knows how to do it. If it really works, they don't want anybody else to know how to do it, then they're not going to talk about it. So this guy, I tend to think that it's going to be I said, when do you think we're going to have a big impact on this oil industry? He said he thinks 3 to 5 years for interpretation. So I'm not going to try to oversell this, but this is something that Shihang did, one of my students. And one of the big problems in seismic is to determine where the salt boundaries are so that you can do salt flooding and velocity analysis in a useful way. So you take a picture of a seismic image and you like to find the boundaries of the salt. And there it is there. And like I said, the input data would not just be this. This is too sloppy. You're really hiding a lot of features. For example, if I want to know who is rich in this room, and I look at you, everyone looks about the same. Everyone has the same kind of, Goodwill clothes type of clothes that I do. So, just looking at people here, the visual image, I'm not going to tell you who's the richest. So maybe Marcos looks kind of rich. He's Italian.
I'm Italian, I'm poor by definition.
No fancy stuff.
I'm Italian, I'm poor by definition.
Yeah, the Italians like to dress, in a fancy way.
Just pretend.
Okay, so anyway, so then I look for other features, not just your images. And what features would I look for? Your profession. How old you are. How many years since your last degree, and what degree was it? So I'd have maybe 6 or 7 features I'd have in each person. And right away, my compass would point to. Okay? And that's what this is. This is like just looking at everybody and trying to figure out who's the richest. No, I think there's features that really tell you who's rich. How old you are, where you got your PhD, or what your last degree was, what your profession is, blah, 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 blah. And one of these is this thing called envelope amplitude, where you look at this over a width of depth, and then you figure out what the maximum amplitude and color code is. So this has a very strong amplitude right there. And then another feature would be instantaneous frequency. Do a short time Fourier transforms, sliding window down here, figure out where the frequency spectrum is and what the highest amplitude frequency is, and color code that. So this is say 100 hertz, and this is 20 hertz, say. So you can see some areas are really high frequency. And then dip angle, so you do a little dip filter on this guy, figure out what the dominant dip is. You can see it kind of follows the structure. And then another one. Now this is really weird. Z coordinate. Those who are doing in geology, pay attention to this. Z coordinate happens to be a huge feature. This says a lot about geology. Why? Because as you start depositing soil, the deeper you go, the more compact you are, and the properties change tremendously, how depth you are. 10 kilometers versus 2 kilometers. And so the seismic properties, the velocities, et cetera, geology changed. And so Z coordinate, believe it or not, was a big deal. We didn't know that until we tried it. X coordinate was an input feature. Anyway, so here's able to do this and take slices of the original seismic data. I'm not showing you the 3D seismic data, just showing you a slice over there. And went on the seismic data, and what did he get? You used a simple, remember the weird architecture? Well, instead of just nodes, you get so many nodes, you kind of replace them with a box of nodes, another box of nodes, and the shape of the box determines something we're going to talk about later, and then finally you get the output. So you can ignore this, and here are the 6 panels for one example, and there's hundreds of these examples that were classified, 6 panels, and hundreds of these 6-panel inputs. So instead of one dog picture, it's like one dog picture and 5 of its features. Salt, no salt. That was the answer. 95% accuracy. So here are the results you got on the seismic data. Seismic data, just using CNN alone, you got this as where your salt was, but if you use this trick I talked about before that he used, this clustering trick, he was able to go from a very rough answer to a very precise answer where the salt boundaries are. And those who are geophysicists know why knowing where the salt is important. Most of you don't know why. And this is on some field data. And this is where the salt is by CNN only, but if you use clustering analysis, he was able to get that down to a much more precise estimate. Processing is also used for processing, and one of the processing steps before exploration has 3 areas in seismology. One is processing the data, seismic processing. The other is interpretation of the data. The third one is reservoir analysis. And Marcos apparently is probably going into the reservoir analysis for petroleum engineers and geologists. And some geophysicists get together and try to do good things. So this would be the processing end. The first people that the raw seismic data is seeing, what they try to do is migrate the data, get these reflectivity images, and then they try to automatically determine where the faults are. And that just gives you a first rough cut. Then you have an interpreter going in and dealing with where the faults are. And that's called coherency cube. And it takes 2.5 hours for training using a neural network to try to automatically get the faults. And coherency is one of the standard methods they use today, and we're going to see if machine learning can beat it out. Let's see what happens. Well, it's a similar architecture as we saw before. The input was it was just these little patches of the 3D seismic images. And these little dots correspond to like a finite difference stencil. That's what goes on in each of these inputs. You'll see what that means later on. It's a filter. It's asking the question, are we at a fault or not? The answer is either yes or no, 1 or 0, or 0 or 1. And once you got trained on this, and you had to have a classified output, once you got trained the W's, then you have the W's and apply it to input data that you never saw before. We had 70-30% accuracy, not us, this is Aramco did this. This is the old way of coherency at 2 different slices of the data cube, and this is the machine learning. Let's compare them in detail. Let's compare this to that. Let's compare that to that and blow it up. So the green, this is the old way of doing it. This is the new way of doing it, of machine learning. So this is machine learning, and this is the old way. So you can see the new way seems to be a little bit better than the old way. And now the other slice, this is before and this is after. This is the after. Let's now put the before. So you can see it's much clearer. So you think this looks remarkable. This came out in geophysics last year. So the person who did this, who led the team to do this, my former student, Yi Lo, and I went up to Yi Lo and I said, I don't believe this, Yi. Because I could easily take an AGC, automatic gain control, probably on this guy, and get everything pulled out pretty well. And he goes, well, no, it works pretty well. It's 75% accuracy. And so then I went, a few months ago, I went to one of the managers at Aramco. I said, this stuff that they did in the labs, you guys use it for production yet? And the manager looked at me and said, no. I said, why not? It looks great. And he goes, well, there's some issues and blah, 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 blah. So it's always, new technology is always slow to be adapted by the oil companies, especially when you already have something that seems to work. So you work for Aramco, right? Do you know about this?
Mm-hmm.
Who works for Aramco? Oh, you did. Oh, you work for Aramco.
Oh, so
Okay, yeah, they're not using this in production as of last spring. Rock samples. You can take images of rocks. what they do is you have a well out there in the middle of the Red Sea, and you bring up these rock samples, you take pictures of them, you like to analyze them automatically. Either you take a core and you start slicing them and take pictures of the slices, and you try to automatically analyze what kind of lithology there is. So what you can do is take these pictures of just JPEG pictures of the cores, and instead of just inputting the pictures, you characterize them by certain features. What they do is take this picture and break it up into the red, green, and blue spectrum. This is green, this is blue, and these are histograms. What this means is this is the number of pixels in this direction. No, this is intensity value. Red pixels of this picture, took it in RGB. They took the red picture out of this guy, and along this axis was the intensity of red. Notice it went all the way from 0 to 255. And this is the number of pixels with that intensity. So this is kind of like a histogram of red pixels in the red picture. Then you took the blue picture, did the same thing. Intensity value versus the number of pixels of that intensity value. And then what they did is they skeletonized this even more. So you took the variance of this curve, you fit out a Gaussian curve, took the variance. There's a third order statistic called skewness. And then you estimated the fourth order statistic called kurtosis, or just scalars. And they did it for all three of these images. These are the only inputs you threw into your training. So you used a real neural network because it's so cheap. And then you trained it on, I think, 7 different types of geology, clay and dirty gray limestone, and different types of geology. And got a result. And these are from limestones, and this is called a confusion matrix. So they took the 50 out of the training set samples, and then they got their W's, and they already had their W's, and then they got the results. And if there are 50 input clays, and the output should have been, the ground truth said there should have been 50 there, but there are only 49. So there's one false negative here. One of them was weathered. Then for the DGL, this is perfect. For the CGL, it wasn't perfect. Only 42 out of the 50 were right, and the rest were misclassified. So it's called a confusion matrix. We'll go through that in more detail. So you can have a way of testing the accuracy of your result. It should be 50-50-50 all on the diagram if you're perfect, but no one's ever perfect. Now, we have a project we started this summer, and the KSA government contacted, who was our friend in the, I forget his name, the water resources professor. Who's the water resources professor? The guy who does drone, yeah, here.
But he left, right? Thompson?
No, the Australian guy. Escapes me. Who's it? He's the guy, the Australian professor in the water resources lab.
Matthew McCabe.
McCabe. Are you a student?
Yeah.
Oh. He contacted McCabe, and then McCabe contacted me, and they want us to, are you involved in this project?
No.
Okay. They want us to analyze this area in northern KSA for a tourist site, and it's an it's an archaeological site. It has these archaeological buildings buried on the other side of this rock mass, and they want to start drilling into the rock mass for tourists, but they want to make sure the thing doesn't fall apart. So they wanted someone to tell us what the density of cracks were in this rock mass. And I said, well, we might be able to do it by doing a drone and then drone survey, and then we can analyze this by machine learning, what the density of vugs are. These vugs, these are holes, how big they are, what the strike of the cracks are. There's cracks and there's vugs here. That could be a big deal when you go in there and try to drill holes in it, for a tourist. Because if it looks like there's a lot of density of cracks here, you don't want to drill over here, but maybe over here where it's not so density. So what I said was, what we can do is use machine learning to do these rosette diagrams that can tell you what the orientation of the cracks are. As you can see, they're mostly here. And we can also do rosette diagrams telling you the density of the bugs here, how many there are, and what the size, average size is, and so on. So each region would have a little scorecard that would be of interest to the engineers. And so my student, Shiheng Feng, already developed a crack analysis code. So you take a picture of an area here, and these are cracks filled in with silicon, and you use machine learning to separate silicon versus non-silicon, and you're able to get the very automatically ones or zeros, and then you can find out what the density of the cracks are automatically. Get these rosette diagrams. And you did a quick analysis, took them just less than an hour, just to find out bugs, not cracks. And it wasn't perfect. It's probably only 50% accuracy. But I told him just give us a quick run at it so I can put it in the proposal. So this would be the idea. You know, the same code he used for finding little GPS markers, he used a portion of it to do a quick and dirty look at the finding bugs. We were in the Republic of Georgia last spring, about a year ago, say. And we did some work with anthropologists with GPR. We did a 3D GPR survey. And the anthropologists want to know where the next site should be for drilling deep. And by drilling deep, 2.5 meters. They can't drill very deep. They can dig deep. But they want to know where. This is a world famous site where they found these the oldest hominids in Europe. They're in the Republic of Georgia. And they found them a little bit over on this side of this box here. We did the survey over the adjacent portion. They want to know where the basalt was, because that's where the hominids were found, near this kind of depression, and they want to know if that depression carried through and region next door to it. And so we did the GPR survey. We took different slices, and the geologists don't know seismic. They don't know how to analyze it. So we let machine learning, using that training process where you talked about, find out where the basalt is, and it did it automatically for us. And where that dip is, that is a likely place where the next site should be buried. So we send this kind of information to the anthropologists, because we don't send this, they won't know what to do with it, but they know what to do with this. Hyperspectral data, and that's what McCabe's group does. He takes drone photos, if not satellite photos, of images of the Earth. And this is an image of trees and roads and stuff like that. And hyperspectral is a camera that can split up the photons into a frequency range of on the order of 500 to 1,000 or more bands. And so the image here really you can decompose into different bands, frequencies or lambda, take your pick. And each type of object here has a different characteristic signature, spectral signature. For example, the trees here, if I were to take this area right here, obviously this is trees, and if I were to grab a horizontal slice of the spectrum here along this axis and display it right here, I get the following. This is lambda. This is the spectrum amplitudes. As lambda increases, then when it gets really large, then the spectrum starts to look like that for different portions of the trees. Each line is saying right here, right here, right here, right here. So it looks like they all have a characteristic feature for trees. And you can do the same thing for fields of alfalfa. You can do the alfalfa fields and get a similar thing. You can do the classified pixels associated with the road. That'll have a different spectral signature, and so on and so forth. So you can see bricks have a different spectral signature here. The metal has a different spectral signature. Asphalt has a different spectral signature. It's asphalt. Trees has a different spectral signature, similar to that. So you train your network one at a time. What's this? Your output is, and this is just for illustration purposes, if it's a tree, it'll be a 1 here and zeros elsewhere. If it's gravel, it's a 1 here and zeros elsewhere. If it's a corn, 1 here and zeros elsewhere, and so on. So you train it that way. You have classified input data. You do the same thing that we talked about earlier, and you train it. And this is an example of a field. It's not the same field here, but different field. This is what the output classification, you can see each color corresponds to a different type of agriculture. And this is ground truth, just for checking. So you can easily tolerate an error like this. And this is a review article in 2019, this year, and presumably an expert wrote it, and quoting him, over the years, machine learning has become the primary tool for analysis of hyperspectral data. And I know that McCabe's group has a hyperspectral camera, right? And I think he's doing it for crop analysis as well, right? Summary, 2 fields, an old field, an old river, and a rather new river meeting for the first time 30 years ago. And they're coming together. And there's 3, in summary, there's 3 types of learning: supervised, unsupervised, reinforcement. I gave you some examples: needles in the haystack of stars, where the needles are stars. Needles in the haystack, where the needles are GPS markers. Needles everywhere, bugs, and other sorts of needles as well. Solvers, rock images. It's the same code for at least 4 of the projects that I've shown you from Shihang. He uses basically the same code. So there's no change in the coding other than what they call hyperparameter things, the size of these filters for the inputs. Which reinforces the idea that machine learning is a field of study that gives computers the ability to learn without having to explicitly program rules. Nothing but a repetition of 2 simple operations, matrix vector multiplication, and a threshold after each layer. What are the challenges? It's a black box. We don't understand it. Convergence. We can't guarantee convergence. Standards. When you get an answer, a pretty picture answer, how do you know which parts are right, which parts are wrong? Is there a standard for analyzing? Best architecture, we don't know that. You might come up with a very different architecture, get just as good a results as Shihang, maybe even better, but you don't know that a priori. It's trial and error basically. What counts, and I found out now, is experience. I thought, my naiveness was, last year when I assigned that project to find GPS markers, I figured, no problem. No. It's usually experience. And a project with new area, new field data, you think, you can do it in a couple months. My experience so far is no. It usually requires an experienced person over many months to get things just right. And how do you assign error bars? Which goes back to your standards. How do you know which is right, which is wrong? What's the future? Large multi-data sets, not just one data set, but like what Marcos is talking about, seismic with well logs, maybe with something else. Not just the raw data, but also what you think are the key characteristics of the features. So you do have to do some extra work on the data to pull out features that are related to how rich each person is that you think are important. One of the things I learned from this ML, this artificial intelligence work is, I'm just amazed at how much cooperation there is in the artificial intelligence community. They put out their data sets out there for everyone to use. They put out all their codes. They have this online publication site called Archive. And maybe it has both good and bad features, but you just go ahead and they take a quick look at it, and if it looks decent, they'll just put it online for you. So they publish your stuff real quickly. And I asked one of the experts out there, how can you do this without going through extensive review? They said, if you tried being in this field, it's so rapidly changing. If you tried being in this field and you waited a year for your paper to be published, you'd be dead. You got to get your stuff out there almost immediately now, because everyone else is doing something, they're ahead of you. You got to do it real quick. And I have some problems with that too. But I think what little experience I've had in the last couple of years working in this area, I think it's going to be the requirement for all good geoscience departments. if not now, the near future. They're going to require all graduate students to take a machine learning course, whether it be one from Sheng Lang or one by your homegrown geoscientist. It's going to eventually be that way. Why do I know that? Because the same thing happened in geophysics with signal processing. In the 50s, the MIT scientists, thanks to geoscientists, started digital signal processing. They were the leaders, the geoscientists, the geophysicists, one of the leaders at MIT, early 50s. So they started doing all this fancy stuff and digital signal processing. And by the 60s, is really the geoscience community was leading the world in applications because they had the money to digitize their data and do something with it. And so by the 70s, late 70s, the really good geoscience departments, only a few of them, required all their students to take a signal processing course. By the 80s, even the intermediate level departments in geoscience were requiring their students to take a digital signal processing course. And when I went to Utah in '85, they made me teach a data processing course. So eventually it goes, yeah, we'll learn from the other departments, but then eventually we're going to adapt that area to our own field, because like I'm going to do in this course. And your department professors are going to start teaching in geoscience machine learning. So I think it's a good idea. All of you guys are trying to do something. And then you get both the good and bad about artificial intelligence. One is humans should be worried about the threat posed by artificial intelligence. I don't know about that. That's science fiction. I think there's a lot more good than evil things associated with that. And he may have blown it, Andrew Ng, when he said machine learning is the new electricity. I think it's going to be somewhere in between. I think maybe the biggest problem right now, maybe that's what he's talking about, is as governments start using machine learning to start intruding into our personal lives and start making us always looking over our shoulders, then that's going to be not a good thing to happen. So, any questions? Okay, I think I'll end this now, but what I'd like to do is I'm going to be leaving for a couple weeks, starting in about a week and a half. I'd like to have some makeup classes. So I would like to have a makeup class tomorrow at noon. Is everyone okay with that? Tomorrow at noon. Here. Bring your lunch. Tomorrow at noon. I'll lecture for about an hour, hour and a half, or hour and 15 minutes. And I'll start on the overdetermined, how to solve overdetermined system equations. These squares methods in about 8 or 2 methods. I'll finish that tomorrow. So tomorrow, here, I'll talk for an hour and 15 minutes. Okay.
So when will you leave for the
A week and a half from now.
next week?
Yeah, I'll be leaving Friday morning next week. I have to go to Europe to apply. And next week we're also going to have labs. You're going to start your first labs. We're going to bring your laptops if you have them. And our lab may not have enough room for all the students here, so only the registered students will be allowed in the lab for sure, and whatever's left over, you know, you can do a coin toss or something. But you're going to do your first labs next week. Probably we'll do it on Thursday. And bring your notebooks, because you're going to get you going on Jupyter Notebook, and we'll have you download some of the machine learning software like Keras and Python. So you'll be doing your first machine learning next week.
Okay.
And whose is this? Is this your son? I don't know where I got that. Is this yours? No. Okay, so see you tomorrow at noon. This is Malaysian Airlines.
把数据那个，因为还是公开的，等于是这些反向的那个特价给200。 火星那个
对啊，
image。
他从那开始写嘛，
对对对。